So today in this video we are going to talk about the certain parameters that we are going to need when we are talking about electrolytic conduction, and the parameters that we will be discussing uh, you might have also learned when you learned about conductors. Okay. Let's three very important parameters that we are going to look in this video is resistance, and then conductance, and finally conductivity. Okay, so before we go into these terms, let's understand a very important law when it comes to conductors. Okay, any type of conductors, be it electronic conductors or be it electrolytic conduction, the very important law is the Ohm's law. Okay. Now, what does this say? Suppose if you have a conductor and you have a voltage E applied across the ends of the conductor, and as a result of which you have I ampere of electricity passing through that. Then, if you want to define what do you mean by resistance, which is written as capital R, it would be simply the ratio of voltage upon the current. Okay, so mathematically we can write Ohm's law as resistance equals to the voltage divided by the current. Okay, so this is a very important relationship, and it's valid for any type of conductor, and so it's important. So now if you talk about the unit of because you know voltage is measured in volts and I is in ampere, so resistance is a quantity whose unit we write it as ohm, ohm, m. Okay, and it's symbolized as this particular symbol. Okay, now in SI unit, if you want to talk ohm, it can be written as kg meter square upon second cube a square. Now you would be wanting to know how we come to this particular unit. It's very simple because we know resistance is voltage upon ampere. So if you write ohm here, ohm would be equal to voltage upon current. Now voltage, we know it's work per unit charge, and work we can write it as kg meter per second square into meter, because work is nothing but force into distance. So this is force plus the distance, and then charge per unit charge. So charge can be written as ampere second, and then you have this ampere already in the equation. So from this you get this particular relationship, that is kg meter square upon second cube a square. So this is the SI form of the ohm. Okay. Now when you calculate the resistance, you usually write it in terms of ohm only. Okay. Now, so this is a very important relationship, that is Ohm's law, and from this we come to the different terms that we are going to look into in this video. Okay, so first inference that we get from this particular Ohm's expression is that the I, that is the current, is inversely proportional to the resistance. Okay, so that is what I have written here. Now, uh, and therefore this inverse of resistance or reciprocal of resistance is what we define as the conductance, is what we define as conductance. Now you might be thinking why we already know what is resistance, why we need to add another terminology called conductance. This is because when you talk about electrolytes, the more appropriate way to define the resistance would be in terms of conductance. Okay, so this current would be directly proportional to conductance. Okay, so this conductance we represent either by a capital C or a capital G, whichever is appropriate. You can use it. Okay, for my discussion here, I'm going to use capital C. So C equals 1 upon R. Okay, now if you talk in terms, so this is what is conductance. Now, what is conductance? Conductance is simply reciprocal of the resistance. Okay, and that's why this is the second important relationship that you should be aware of. Now, if you talk about the unit of conductance, it's very simple because we know R, the unit is ohm. So, unit of conductance is simply per ohm. Okay, per ohm, and per ohm can be written as Siemens, represented as capital S, and it's also equivalent to the ohm written in the reverse order, so it's called as mho. So these are the three different ways in which you can put the unit for conductance. So in electrolytes, we more talk in terms of conductance of the electrolyte rather than using the term resistance when it comes to electrolytes. Now, like the observation that we see here, that is current is inversely proportional to resistance. Similarly, another observation that comes as a result of various studies is that this resistance is kind of directly proportional to the length of the conductor and inversely proportional to the area of the conductor. So this is an observation similar to the observation that we see here, that is current is inversely proportional to resistance, which actually is a kind of inference that we get from the Ohm's law. However, this is an observation where we find that the resistance of a conductor is directly proportional to its length and inversely proportional to its cross-sectional area. So this is basically the cross-sectional area. So this is cross-sectional area. Okay. So now if you remove this proportionality symbol with equal to sign, you know that we have to add a proportionality constant. So in this case, we use a constant called rho. Rho is a Greek letter. Okay, rho. Okay, so this rho, this constant, is called as the specific resistance or resistivity. Specific resistance or resistivity. Now, if you would like to define what is resistivity, you can simply define in this way. Like if you substitute the L as 1 centimeter, A as 1 centimeter square, then what we see here is the resistivity is equal to the resistance. So we can define resistivity or specific resistance as equal to resistance of a conductor of 1 centimeter length and 1 centimeter square area. Or in other words, if you talk in terms of volume, we can say resistance of 1 centimeter cube or meter cube. If it's SI unit, we will write meter cube. So specific resistance or resistivity is equal to the resistance of 1 centimeter cube or meter cube, 1 meter cube of the conductor. So this way you can easily define what is specific resistance or resistivity. Now, in terms of the useful parameter, uh, rather than the specific resistance or resistivity, the important term that we come across is this particular term, that is specific conductivity, or in other words conductivity, which is basically the reciprocal of resistivity. Now, one of the reciprocal we just now learned. What was that? It's simply reciprocal of resistance was equal to your conductance. Okay. Similarly, the reciprocal of resistivity we just now defined as rho is simply what you call it as the specific conductivity, or simply you can call it as conductivity. Now it's represented using a Greek letter, this kind of inverted K kind of thing. You simply write in this particular fashion. This is called as kappa. Okay, or more conveniently, you can simply write capital K, which also denote the conductivity. So, in other words, you get kappa, or conductivity is equal to 1 upon rho. So, this is another important relationship that you should be knowing. Okay, so coming after knowing this, we just now learned a relationship which was nothing but R is equal to rho L by A. Okay, this is what we just now learned, and using this expression we tried to define the resistivity. Okay, now if we rearrange this particular equation, we can simply bring it here and bring it here. So you get 1 upon rho equals 1 upon R L upon A. Okay, as a result, what happened? You will see that now 1 upon rho is nothing but your conductivity, which is K, and 1 upon R is conductance, which is capital C. So what you see here, kappa or K, conductivity, is equal to conductance multiplied by L upon A. Okay, now if you want to define conductivity, you can define it in a similar way as we define the resistivity. That means if you take a conductor having a length of 1 centimeter, or and a cross-sectional area of 1 centimeter square, then your K would be equal to capital C, or in other words, conductivity would be equal to conductance. So in other words, if you define conductivity, conductivity is equal to conductance of a conductor of length 1 centimeter and cross-sectional area of 1 centimeter square. In terms of volume, you can write simply conductivity is equal to conductance of a conductor of volume 1 centimeter cube or 1 meter cube. Okay, so any way you can define this particular conductivity in this particular manner. Okay, so another important thing is units of resistivity and conductance. Now from the expression only we get this. So from this expression, if you if you want to know the unit of rho, you simply bring it here, and bring this L by A on this side. So you'll get expression something like this: rho is equal to R A by L. Now rho we know, R we know is ohm, A is meter square upon meter. So simply resistivity unit is nothing but ohm meter, or in CGS unit would be ohm centimeter. Okay, and 1 ohm meter is equal to 100 ohm centimeter, because we know 1 meter is equal to 100 centimeters. So that's how you get this particular relationship. Now if you want to talk about the unit of conductivity, conductivity we know is reciprocal of resistivity. So resistivity we know it's ohm meter, and therefore conductivity would be per ohm per meter. And per ohm we know we can represent as Siemens. So it is Siemens per meter. In CGS unit we can write Siemens per centimeter. Now 1 Siemens per centimeter is equal to 100 Siemens per meter. Now it's reciprocal, that's why the 100 factor came towards the meter side. Okay, so these are some of the very important parameters that we should be aware of when it comes to electrolytes or electrolytic conductors. So hope you have understood all these three important terms, that is resistance, conductance and conductivity. So in the next video, we will talk more different parameters of the of this relating to electrolytic conduction. So thank you for watching. See you in the next video.